Hello, everyone. My name is Javier Arroyo. I'm a research and development engineer at WIDOCO, which stands for We Do Control. You can always visit our website and check out more information here at widoco.io. Today, we are going to walk through this tutorial on building control with reinforcement learning using the building optimization testing framework, the so-called BOPTEST environment. So what we are going to learn with this tutorial is what is reinforcement learning, how it works, how it can be used for the application of building energy management. And we are also going to learn the most famous, it's a very popular standard for representing general reinforcement learning problems, which is called Gymnasium. And you are also going to learn what is the BOPTEST framework and its Gym interface, which is very useful to test controllers in general for building energy management. But today we are going to have a special focus on reinforcement learning. So just a side note, this tutorial is prepared for BOPTEST version 0.6, and we are going to use the so-called BOPTEST service, which is a service that is prepared so as to have BOPTEST readily available without you having to install it in your laptops. But you could also work with Docker containers to spin up BOPTEST test cases that work as virtual buildings, and you could work with those buildings locally in your environment. So the outline is we're going to start with a brief background on what is reinforcement learning and how this can be applied to buildings. Then we're going to learn Gymnasium, which is the standard I was talking about, then BOPTEST, and then we are going to see how these two tools work together in the so-called BOPTEST-Gym environment. And we are going to do some exercises with BOPTEST-Gym. So every time you see a spark here, that means that is a fill in the blank exercise. So you can try out some of the things that you've learned in the previous sections. Now, let's start with the brief introduction to reinforcement learning. I should mention first the tutorial, I will say it's self-explanatory, so you should be able to follow without even the video. But here we are going to go explaining the main concepts, so it's even easier for you to understand. So what is reinforcement learning in the first place? Well, this is a branch of machine learning. Machine learning has three main branches: unsupervised learning, supervised learning, and reinforcement learning. In the first two, we learn from static data. So the difference between unsupervised and supervised is whether our data has tags. So in unsupervised learning, our data has no tags. So it has to group the data somehow. So I think a very good example would be the Google Photos classifier. So Google Photos has not the information of who are the people that appear in your pictures. And somehow it has to figure out how to group those pictures by people so that you can later on look for the pictures that in which one of your friends appear. So it classifies the photos based on information without those photos being labeled. Whereas in supervised learning, you do have labels of those data, and you're more interested in doing things like regression. Okay, anyway, like those work with static data. Whereas in reinforcement learning, what we are interested in is in deriving a control policy. What we want is to learn from dynamic data, so dynamic that we get from a process. So in reinforcement learning, we have what is called the agent and the environment. The agent is the reinforcement learning agent, is the brain, is the reinforcement learning algorithm that is going to try to learn the environment by interacting with it empirically. So it's going to send some actions and it's going to receive in return some rewards and observations. And from this information is going to have to learn what is the optimal or the hopefully optimal control policy to drive this environment. So we're putting here an example in which in which an agent has to learn how to grab a stick. So the agent is the dog, and the dog has to learn how to grab a stick from the environment. The environment is everything surrounding the dog. So that would mean the environment is the human throwing the stick. And here an observation would be the image of that human throwing the stick. And the dog has to learn that, okay, whenever the human is about to throw the stick, it has to start running, it has to grab the stick and come back. And then the reward would be, for instance, could be a cookie if the dog has walked back with the stick. And maybe there's no cookie if the dog hasn't walked back with the stick. And then the dog learns, okay, if I want to get a cookie, I have to do this. So that's actually how reinforcement learning works. And it may sound silly from this simple example, right? But if you extrapolate this to any process, any system, you realize this is a very powerful concept in which we fix or we standardize the API between the agent and the environment. And therefore, with the same algorithm in the agent, you can learn several environments. So maybe the same algorithm we've set here to learn the dog to grab the stick could be used for an industrial process to optimize the performance and therefore to reduce energy use or to reduce costs. So one important note is being added here is that you have to be careful with what is called an observation and state, because sometimes it's called distinctively for many applications, and it's not exactly the same. The state is the actual full representation of the environment, and the observation may be a subset of that representation. It's not always that the observation can cover the full state. And that's always the case in continuous processes. So if a variable is a continuum, I cannot fully vectorize that variable. So that's just a side note. I'm just saying because that's one of the cases that we will have with buildings. For instance, a typical observation is the temperature, and we cannot provide a vector, an observation space with all values of the temperature, because that's a continuum. It's an infinite amount of values that we will need. Just as curiosity, a few applications of or a few achievements of reinforcement learning in recent times. It has been able to defeat the best player of AlphaGo, which is a strategic game, and it's a special milestone because it's the AlphaGo game. It's attributed to need some creativity to be played. So that's something, that's a quality that has been usually attributed only to humans, and now we get that with some reinforcement learning algorithms we can learn that. So that's quite impressive. So that's just a curiosity. There's a link here to a Netflix documentary, which is quite nice to watch, I would say. So what we have learned so far, a few quick facts, is that reinforcement learning is a category of machine learning, that it learns from dynamic data. So it keeps interacting with an environment, and from tuples of state, action, rewards, it should be able to learn an optimal control policy and to optimize that process. So what all this has to do with building energy management is that there's been a recent application to this domain. So if you see here in this graph, you are seeing the number of publications and citations for optimal control in buildings during the last decades. So there's been a clear growing interest in learning how to optimally control the energy of in buildings, because we are clearly we are clearly under optimized on this regard, in the sense that we could better control buildings using more advanced control algorithms like predictive control or reinforcement learning. So it's also important to mention that this is especially interesting since buildings in the end use over one third of the final energy use worldwide. So if we are miscontrolling these processes, it's a lot of energy we are wasting, and therefore we want to do better with these more advanced controllers that are available to us. But there's a lot to do. So far, we are only using rule-based controllers, and therefore there's this growing interest in applying these more modern algorithms. And most of it has been applied to in research. There's some that has been applied to in practice, but not a lot. And in research, the focus has gone to demand response settings for applying reinforcement learning to buildings. So demand response means trying to adapt our demand to the needs of the grid, and so use more energy whenever there is more renewables into the grid. You can see here a small map on how this research track has evolved over time, with the first applications of reinforcement learning to buildings dating on 2005, 2006. Here there's quite an achievement by Chen et al. On reducing the amount of data that is required to learn an agent for the application in buildings, which is critical because we cannot indefinitely interact with the building just to learn from it. So we have limited amounts of data. So most of the research goes to expedite learning. So to see how we can learn with less data. This is something we are going to see in a few moments. And here it's been mentioned that this is the reasons why we have come back to or the reasons why there is so much interest now on reinforcement learning is because of the evolution of deep learning that can greatly help reinforcement learning. We have way more data than before, and we have much more computational power than before. So those are factors that are making us all look into the new possibilities with reinforcement learning. And here you have some links to repositories that have somehow already considered the possibility of implementing reinforcement learning in buildings. One very interesting one is CityLearn, which is in a sense quite similar to what we are going to learn today, but more applied to urban scale. So not to individual buildings, but to districts. In there, what we want to do is to apply reinforcement learning to flatten the demand of the district. So to provide demand response in a way in a urban scale. There are others like Gym E+, Gym, BOPTEST, different possibilities. Some of them have Python backend for modeling the building. Some of them have an E+, Energy Plus backend. And in our case, we are going to learn BOPTEST-Gym, which has as backend BOPTEST, which has as a very backend Modelica to model the physics of those buildings. So I would say what sets apart BOPTEST from other frameworks that are used to model and simulate buildings is that with BOPTEST, you have buildings that are very reliable. We model the physics into very detail. If you want to know more about BOPTEST, you can just go to the GitHub page, or you could go to the main website of BOPTEST here, where you have a full description of the framework, and also what is a list of available test cases that you can run. Okay, before going into BOPTEST, let's jump into what is the Gymnasium standard, because that's what we are going to be running in our tutorial today. So Gymnasium is a software library that gathers a collection of tasks. So these tasks are called environments. So actually what Gymnasium is providing is a collection of environments. It's not providing reinforcement learning agents. It's providing environments. So Gymnasium will be providing a collection of this site here. And then it's up to the user of Gymnasium to provide or to test different reinforcement learning agents into into those environments. But what is very powerful of this Gymnasium is that it's providing the standard, it's providing a standard API in Python to interact with these environments, such that we can be sure that we can interact with one or many environments in the collection that they provide. And this standard is as follows. So I'm putting here like the two main methods that this standard is it's agreeing on, which is the first one is to reset the environment. So when after instantiating one environment, we'll later see how we do that, we can reset it to bring it to a logical state. And in return, we get the observation, that very first observation before starting with that environment. And the second one is once we get the observation, we expect our our agent to derive an action from that observation and send the action to the environment. So once we get the observation, we compute our action and we step the environment with that action. And in return, we are going to get, again, the next observation, but this time also the reward from going from the previous observation to the new observation, and also whether the environment is terminated or truncated. Terminated means the goal of the environment has been reached, so we naturally terminate that environment, or we truncate it. So we finish it before we reach the end of the episode of the environment, because because we want to finish before, because maybe we are not interested in the last part or in the last steps, because we are wandering around from what is the interesting data we want to grasp from the environment. And then there is an optional information return argument as well, which is just to provide any information about how the environment has evolved. Now, something I should mention, and there's a couple of things here to add, is that Gymnasium relies very much in the concept of episodes of experience. So the idea is that we reset to the beginning of an episode, our environment, and then we interact for that episode, and then we reset again to another episode. So it can happen, but it's rare to see environments that are continuum, that just have one long episode. Instead, we typically want to have like fractions. And we jump from one fraction to the other with the reset method. And another thing I wanted to say is that Gymnasium is providing a standard. So it's not that we can use only the collection from the collection that they provide. I'm gonna show you here. So if we click in the Gymnasium here, you see their collection, different types of environments. But since they provide the standard, you can also build your own environments and learn reinforcement learning to those environments. And that's exactly what we are going to do with BOPTEST-Gym. So we are going to see here how we can use the Gymnasium standard to interact with buildings of the BOPTEST framework. Hopefully that'll be more clear in a few minutes. Okay, for start, we're just going to start installing Gymnasium. So first time we run install, it may take a bit long. And for start, we are just going to learn how to interact with one of the environments that Gymnasium provides, which is the card pole example. Okay. So it's installing Gymnasium. Okay, it has been installed already. So the carpal example is basically a pendulum that we want to keep erected by applying forces at the card on the bottom. So it's a frictionless card. We can apply a force to the right or the left. And the idea is that you receive a reward of 1 every time a step that you keep the pendulum upright. So just to get familiar with how Gymnasium works, first thing you need to do is to import Gymnasium to make the card pole environment. And then we decide that the maximum number of episodes we want to run is 10. And while in every episode, while this episode is not done, we keep applying an action that in this case, just for the sake of illustration, we are going to get to be random. So in Gymnasium environments, typically you can just use this. So once the environment is instantiated, you can access the action space and you can sample the action space. So this is just going to return a random action in the format that is expected for that environment. Sorry. So with that action, we can just input that action to the environment and step with that action. And then we will receive the observation reward, terminated, truncated info that I was talking about before. Then we compute whether the episode is done, either because it has been terminated or truncated. And then we step one reward. We step forward and add the reward in case we've gotten one, because we have still survived during this control step with the pendulum upright. And then we are printing for all those episodes. For those 10 episodes, we are printing what is the total reward we've gotten. We may not expect to get a lot of rewards since we are just applying random actions to the pendulum. So this is a random thing where we will be getting. And you see that for every for every episode, we get a different reward depending on how much or how long this has lasted. So if we were to compute this again, we will get a different amount for every episode because it's just random. Now, the first fill in blank exercise is just for you to warm up. So in this exercise, what I'd like you to do is that you have the same exercise as before, so the same environment, the pendulum, and you will see here a blank that you need to fill in order to compute a control algorithm that is a bit more smart than just applying a random control action. So you can see already here, I'm extracting for you the observation space. So the observation space is has a dimension of 4. First value is the card position, then the card velocity, and then we have angular coordinates. So we have the pole angle and we have the pole velocity. And then we have the same test for running the environment as before. The idea is that here you compose some control logic that decides on the force, on the direction of the force based on one of these observations. I can advise you to use the pole angle, and here you see if what it means to apply an action to the left or to the right. So if you take action 0, that means the force will go to the left. If you take action 1, the force will go to the right. And you can decide on that based just on the whether the angle is positive or negative. So if you implement that all right, and also you need to add here a line to use that control algorithm. If you implement that all right, you should expect these total rewards per episode of experience to last in average longer than just applying a random control action. So I'll leave that to you. Hopefully hopefully you can play around and learn a bit how to work with Gymnasium. But I'll myself go straight to the next section, to the next part of the tutorial, which is learning what is the billing optimization testing framework. So the main use case of BOPTEST, I'm going to explain that with this figure, is one of a control developer that wants to implement a controller for billing energy management, and for whatever reason cannot interact directly with the billing, or just because it's cheaper to interact with simulations than with real billings, wants to test his or her controller in simulation. So BOPTEST provides two main things. It provides a suite, a menu of billing emulators that are very detailed, very reliable. And also it provides a runtime environment that can simulate those billings. So the idea is that the user picks one of those emulators and deploys that along with the runtime environment in a Docker container, either in the cloud, as we are going to do, or in your Docker daemon and your local host. And then it can run echo simulation, sending control actions and receiving measurements from that virtual building. So after some interaction, after an episode of experience, as we were calling before, we can also get a report from the runtime environment as to know what are the main KPIs of that interaction, of that control logic. So the test case is basically what is so-called a functional mockup unit, which is a model encapsulated into a file, which follows a standard, the functional mockup interface standard for simulation, which is basically a detailed building, a detailed building model. Then for every emulator, you also have boundary condition data. So you have weather data, pricing, occupancy schedules that come along with the model, and that are compiled all together with the model. And then you also get an API for interacting with BOPTEST, such that it's standardized the way you send control signals and receive control signals. So you can see here, if we click there on the link, you can see what are the commands that you can run. So here you have commands to get available test cases, to start a test case, to initialize a test case, to get what are the measurements that we can read from the building, the inputs, to get the results after the simulation, to get key performance indicators up to the point that we have simulated, and so on. You see there are not as many. The idea here is to have the least possible amount of API calls that allow full freedom to do anything you need with the building. So the basic workflow that we have is that we select a test case, we select one of the testing scenarios, which are standardized. Typically, we have peak heating period scenario, typical heating period, peak cooling period, typical cooling period. Those are pre-computed based on the data of that building that we are working with. And they last for 2 weeks. So that's standardized. So we can compare different results for different scenarios. But it's not mandatory to run a simulation in one of the scenarios. You could run outside of the scenarios just to learn a policy or a control policy, to train a gray box model, for instance. For different reasons, you may want to be outside of the testing scenarios. Then you set the parameters for cost simulation. So what is the control step length that we want to interact with? What is the forecast horizon if we want to request weather forecast, for instance, every control step for predictive controllers, these kind of things. Run the test case scenario in a cost simulation after you have set the parameters, and then evaluate. So we just call the API that was saying get KPIs, and that will give you an evaluation. Okay, So I was saying before, you can see here the repository of currently available test cases. You can see here a small description. And if you go below, you can also see the time periods. What are the electricity price profiles available that you can also set through the API. If you want to see a full description of the test case, you can just jump into that link, and then you have data about the building envelope, about the HVAC system design, about what is the control included in the building, what are the points that you can read and that you can override. So what are those values that you can play with? What is the forecast that you could get if you needed to? And here also the scenario info in more detail than in the previous website. So an important thing I didn't mention about BOPTEST is that it always comes along with the baseline controller, which is meant to be representative of the building we are working with. So that means that I can decide either to override one of the control points, or I can just run the simulation in free floating and without overriding anything, and then it will give me still some output that follows the rule-based controller that is implemented in that building. That is what is so-called the baseline controller. So that is also something that is mentioned in the documentation for every emulator. So here you can see HVAC system design, and then here rule-based or local loop controllers. If included, it says, but it's always included. So you always have a rule-based controller that is called baseline controller. So you can just gather data from that baseline controller. If you're not interested in exciting the building for getting more rich data, for instance, you could just run the baseline controller and get the default control behavior, let's say. So now we are first going to connect with a test case of BOPTEST. This is the so-called BOPTEST hydronic heat pump case, which is actually the one I was showing you before. What you can see here is the URL to BOPTEST service. So BOPTEST service is readily available in the cloud to spin one of the test cases in a Docker container. So you can connect to it through this URL here and just select the test case you want. And that what it's going to do is just to spin a Docker container with the test case there on the cloud, but it remains the same as, or almost the same, it remains the same as if you were to deploy it locally in your laptop. So I said almost the same because of a couple of things. Like if you deploy it locally in your laptop, of course, it's going to be faster, but you need a bit of knowledge on Docker, and you need to have Docker installed locally. And it's going to be faster, of course, because you don't have to interact with the cloud. But and it has almost the same API. So all API calls are exactly the same, except for the fact that we have to put here the URL and the test ID. So if you were deploying it locally, you could just use the URL and that would work. But since we are working with the cloud, we need a unique identifier to know what is our specific test case there in the cloud. Anyways, here you have in BOPTEST, you have documentation to know better how to interact with it locally or remotely if you wanted to. I want just to point you to one of the tabs here in training. You have more documentation on how to interact with BOPTEST test cases. So hopefully that's useful. But for us today, we are going to work with service version. So we just go for it, run the first cell. We get our test case. We get the name of the test case just to prove that we have connected to it. And indeed, this is returning the name to be BOPTEST hydronic heat pump case, which is expected because it's the one we have selected. So now we are connected to one of the test cases, which I should explain before moving forward, because this is going to be the one we are going to use throughout the tutorial, to be using throughout the tutorial. So this is a very simple building. It's a residential dwelling. It's modeled as a single zone, and it has floor heating. So the floor heating is connected to a air-to-water heat pump, and the controls that are implemented are basic thermostatic controls. So it basically reads the temperature of the zone, and this C1 is going to activate the heating, so the motor of the heat pump, of the compressor of the heat pump, in case heating is required using a PI. And then this controller 2 is basically going to activate the circulation pump of the emission system, so floor heating, and also the fan in the evaporator of the heat pump in case this motor is activated. So there's like first layer of control and second layer. And what is handy of this controller is that we can easily control the test case just by overriding the modulation of the heat pump, which is basically what this C1 is deciding. So this is C1, this is the control 1. Basically, it's a PI controller that decides on this override heat pump modulation, Y, and we can just ourselves decide to override this directly externally, and then all other control would follow as required, because this C2 is the slave of C1. It's going to follow or it's going to activate whatever is needed if heating is required, if you or the modulation of the heat pump is higher than 0. So what I'm trying to say is there is one control action, which is the modulation of the heat pump that goes from 0 to 1. 0 means no heating, 1 means full heating. Now, there could be other possibilities, like if we want to get information about what we can override in this building and what we can measure, we can just request to get the inputs and the measurements, and that will return a full list, which is also available sorry, in the list of test cases here. So here in the documentation, you always have the full list of inputs, so actions that you can override, and outputs that you can read with a description. Now, since we have learned how to use BOPTEST or how to interact with it, there is a very first exercise on the usage of BOPTEST, where you have to create your own controller. It's a very simple controller that I'm asking to here. It's a proportional controller. So the idea is that you fill this gap here to compute control based on a proportional setting. So we have a set point that we want to reach, and then we have a proportional gain. And every control step, we are going to receive a measurement Y, and we want to, based on that measurement, we want to decide on the value. So if you are below the set point, you may want to increase the value. If you are above the set point, you want to decrease the value. So there is some default values here you could use, or you could tune those. But what matters here is that you control this control logic. It's very simple, with if-else statement should be enough. Now, the next cell is to test your controller. The next cell is quite long, but you shouldn't be concerned about it, because it's just some plotting functionality here and the cost simulation loop. So here what we are going to do is to, sorry. Here what we are going to do is to initialize the scenario. So we are choosing the peak heating period and the electricity pricing to be dynamic. So that means that there is a profile for electricity pricing that goes from low to high pricing every day. And then you also have here the start time days, which you get from the return of the setting the scenario. And then we set the control step to be 1 hour. So every hour we are deciding on on that control action. We apply that action and then we wait for 1 hour and then we repeat the process. We decide one control action and we implement it. And we apply that for 24 hours here. This is just to print on the loop what is the reading of the temperature of the zone. And here also what is the time, the simulation time. So you can know what's going on. And it's only at the end that we are going to use the plotting functionality of this method I mentioned before, and we are going to plot it. So if you implement that, you should see something similar to this, not exactly the same because it may depend on your controller. So what you can see in the plot are the comfort bounds that are set in BOPTEST, which you see are varying because it depends on whether the house is occupied or unoccupied, that you want to have a broader or more tight comfort range. And then you see in orange the evolution of the temperature of the zone. Now, here below you see the heat pump modulation signal that is set by the controller. And it's clear that whenever we turn it on, we increase temperature. If we turn it off, temperature decreases, of course, because we are in the peak heating period. So temperature outside, as you can see at the bottom plot, it's quite low. And the last line you can see is the yellow line, which is the solar irradiation. So feel free to play around as much as you like, implement the controller and have a lot of fun. And then after you finish, you could just stop the test case, just not to overwhelm the server in case there are too many test cases spinning. Okay, now let's go to BOPTEST-Gym. We have learned what is gym, what is gymnasium, and we have learned what is BOPTEST. So as you can envision, as you can guess, BOPTEST-Gym is a framework that merges both of them. Basically, what it's doing is accommodating the API of BOPTEST to the standard of Gymnasium. So we can use the BOPTEST emulators directly with the gym standard. So we can directly do, we can directly call the reset and the step method, and that is going to work with BOPTEST-Gym. Now, for working with BOPTEST-Gym, we need to install this, stable baselines and NumPy, one of the specific versions. And here I'm going to explain a bit how it works. So this is what I've just explained. The particular hyperparameter that is important when we initialize an environment with BOPTEST-Gym is the test case, because that one is going to point to the test case that we want to run with. And then the state of the emulator or of the environment, it can have a time component. So we can read the time if that was interesting for the environment or for the agent. And then it has a set of exogenous components. So those measurements or forecasting variables if we needed to, like ambient temperature or what is the current temperature in the zone. And then for the actions, you can have all the variables that you can input to the emulator. So when we reset the environment, we are going to warm it up to the beginning of one of the scenarios, or we are going to warm it up to any time throughout the year, depending on what we choose. And then the step method is going to send the action to the environment, and that action is going to be sent to BOPTEST. Sorry, it seems I need to restart session for some reason. Yeah, sometimes this happens. Happens when running through Chrome, not through Firefox for some reason. Otherwise, I think it's resolved just by restarting. And it sends the action to the environment and simulates, and you get back the observation space. again, and also the reward. So it works just as a regular gym environment. Now, what we want to do is to clone BOPTEST-Gym. So just get a copy of the repository of the BOPTEST-Gym service version, and from there we are going to import BOPTEST-Gym, and we are going to instantiate our first BOPTEST-Gym environment. As you can see here, the main hyperparameter is this Bestes hydronic heat pump case. Then we decide the action space to be the modulation of the heat pump with this list here. Then we design the observation space to be this variable here, which is the temperature of the zone. And what follows is just a tuple explaining or showing what is the expected minimum and maximum value of that variable. This is just for normalization purposes. That's why for observations, we require a dictionary instead as in actions that what we have is a list, because the actions that the minimum and maximum value of the actions can be derived from the BOPTEST framework itself, but that's not the case for the observations. So we need to provide that information. Now, if we decide to start with a random start time, that means every time we reset an episode, we are going to randomly allocate the emulator in any time of the year. And otherwise, we are going to decide on a start time. And then every time we restart the environment, we are going to start here. So this is the time of the year in seconds. And that means we are starting the 31st day of the year after that 31st day. So that's the 1st of February. Then the maximum episode length. So we want the episode to finish after maximum 24 hours. And the warm-up period, we want the episode to warm up. So the emulator to run with the baseline controller for 24 hours right before the beginning of the episode to bring our emulator to a logical initial state. And the step period to be 1 hour as before. So that's what I've explained. Right now here you have a view on how the whole machinery works. So this is just for illustrating what you're doing with BOPTEST-Gym. At the very left-hand side, I'm going to explain this very quickly, but at the left-hand side, you have yourself, the user, who decides to, through the reinforcement learning agent, to interact with an environment. And then you have the gym environment where you can to which you can send the reset and step methods, which are the most common to be sent. And after that, BOPTEST-Gym, what it's going to do is that it's going to accommodate those commands to the commands of the BOPTEST. So if we reset, what we're going to do is basically to initialize and to get forecast if needed, to return state. And then in the episode loop, every time we step, we are going to call advance. Well, not we, but BOPTEST-Gym is going to call advance, get forecast if needed, get KPIs if needed, and then we are going to compute the reward and whether the episode is done and return the state and reward. So as we have said, first thing we want to do with every gym environment is to reset it, to bring it to logical state. So if we call here reset, we are going to reset it according to the specifications we had defined when we deployed, or when we, when we instantiated the environment. That's the word. So we only have one observation. So that's the temperature that we want to transform from Kelvins to Celsius. And we see that if we reset it for the first day of February, we get that after 1 day of warm-up period, our zone temperature is 21 degrees. And we can see that, in fact, the start time of the environment is the 31st day of the year, if we translate that from seconds to, from seconds to days. Notice that for every environment, we can print what is the observation and the action space. You can see here, box means a continuous environment of only one dimension. and we have an observation space that is continuous because it's a temperature, and these are the minimum and maximum values expected that we have set before in the when we instantiated the environment. And for the action, it's again a continuous that goes from 0 to 1 because that's a modulation of the heat pump. Now, we could print the environment, and there is some printing functionality here that will display a lot of information about BOPTEST and the BOPTEST-Gym environment. So first, BOPTEST case information, and then, and then at the bottom here, some other information more specific to the gym environment. So that could be handy. And what is very important is that BOPTEST-Gym comes with some functionality to discretize and normalize, which is very handy because we can learn faster if we discretize our environment. So what we are doing we are importing the discretized action wrapper such that we transform the action environment the action space of the environment to be, instead of continuous, to have just one bin, so two possible actions. So we have transformed it to be discrete of dimension 2. And we can always access the unwrapped environment if we wanted, and you can see that in that case, if we print the action space, we get that is still continuous. Now, the first fill-in-the-blank exercise for BOPTEST-Gym is to implement a similar controller than the one that you have implemented before for BOPTEST, where we were using directly the step method and the API of BOPTEST in general. We want to use now the terminology of BOPTEST-Gym or Gymnasium in general. You can see already that here there is something that could seem counterintuitive, which is that the method to request the control action is not control, it's called predict. And that's because I want you to get yourselves familiar already with the Gymnasium standard. In the Gymnasium standard, an agent, when you require an agent to return you with an action based on observation, you don't use the method control. You use the method predict because the agent is typically a model, a neural network, a deep neural network, probably with that is going to return you somehow that action set. That's why it's called predict. But the logic that you should implement here is very similar. In this case, we have this set as an attribute of our simple controller, and we want to implement a logic that returns an action based on that, based on the observation. So here we read the observation. If observation, which is the temperature of the zone, as we have defined it, it's below a value, then we apply an action that is going to warm up the building, and the other way around. Basically, we can go from 0 to 1, so either we decide to be 0 or 1. So here you have the co-simulation loop that you can implement. Here you don't have to touch anything, but hopefully on the go, you can see how your control logic works. So we are going to be printing all the time the temperature in the zone. Now we get to the most juicy part of the tutorial, where we are going to go beyond implementing a basic rule-based control action in Gymnasium for BOPTEST. We are going to try to implement our own reinforcement learning agent. So this is going quite deep into reinforcement learning, and I'm just going to explain the intuition to it. If you need further information, you always can access the more detailed explanation that you get here at the bottom. So this is a more formal description of how reinforcement learning works if you get lost. And also here there's some references to books and also other materials for understanding how reinforcement learning works. But I'm going to try to quickly explain how we are going to develop this reinforcement learning agent. We are going to use the so-called Q learning algorithm. And we are going to formulate, therefore, our problem as a Markov decision process. So for every state of our building, we apply an action, and then we receive in return a reward and a next action. So Q-learning basically is based on bootstrapping to represent what is the value of being in a specific state and taking a specific action. So it's going to say that our the value of being into a state S an action A and take an action A from there, it's the reward that we obtain plus a discounted the discounted maximum of the next the Q value in the next state and next action. So that's what is called bootstrapping, is the Bellman optimality equation, and it's useful to formulate the problem in a way that we can learn very quickly. Okay, so this will be, for instance, a representation of what I'm trying to explain here, which is the Q function of whatever process. And here we can see that it's just, we have just one dimension for the observation and for the action space, just for illustration purposes. So the Q function will tell us that if we are in state S and we come and we want to decide on an action, basically we want to take this action because it's the one that has the highest value, the highest QSA value. Now, the question comes, that's great as far as we have the Q function, but how do we get to that Q function? Well, what we are going to do is we are going to use this formula here. So we are going to keep updating Q based on empirical interactions. So we are going to start with an initialized Q. It could be a flattened function. And then every now and then, let's say every few steps of experience with the environment, we are going to update that Q with what is called the temporal difference. So the difference between what is my current value at QSA and the value that we empirically observe. This is something that we are getting from the environment. So we get the reward, and we can know what is the maximum value of Q because we already have that estimate. It's true in the beginning it's going to be very bad because it's just an estimate. Maybe it's flat, so this is not saying much, but with time, it will be sapient as to resemble what is reality. So we keep interacting and sapienting our function until it gets more and more accurate. And once we have so, we have something like this such that we can decide on the actions to be taken. Now, there is another thing that is very relevant to reinforcement learning, which is the exploration-exploitation dilemma. It's coming to say like, okay, imagine now I have a well-shaped function. Do I want to take the action that leads to the most expected cumulative reward, which is this one, and keep applying that action always? So do I want to follow the policy that I have learned, or do I want to explore what is the possibility with other actions that maybe I didn't learn and could lead to a higher expected cumulative return? So the answer to that is, it's not straightforward. It's in the end a trade-off that you have to make. You have to exploit because you want to optimize your process, but you have to keep exploring somehow, applying some random actions. So a typical approach that is being used for this is the epsilon greedy algorithm, where we start applying always a random action. So the probability of the greedy action in the very beginning is very low. So we take random actions in the very beginning, and then we keep decreasing over time that probability of random actions until we are more confident we have learned a policy that works, that is good enough. And at some point, we just apply very small random actions once in a while. But this could go to zero as well. but it's usually better to keep some chances of exploring after a period. So all this I've explained with words, it's implemented here in this Q-learning agent. You can go through it to understand. I'm not going to go into the details. Hopefully it's self-explanatory with what I've said. Just going to say there are two methods. One to learn, and in which you can set the number of episodes you want to learn, and then another one to predict. So if you just want to an action with an epsilon greedy policy, after having learned the environment, you can just use the predict method. Now I'm going to explain how to apply this to BOPTEST-Gym. So the idea in BOPTEST is that we want to reduce thermal discomfort, so the periods of time we are outside a comfort range, by applying some power. This power is driven in our example before by the modulation of the heat pump. So we want to define a reward function in our environment that tries to minimize what is the discomfort and energy use. So this is something we can do with the functionality of BOPTEST-Gym. We just have to inherit the BOPTEST-Gym environment and change the get reward method. That's a standard. So get reward method comes along, the BOPTEST-Gym environment comes along with a default get reward method, but here we want to customize it. And we are going to use the KPI, get KPI call to get all KPIs. And from that one, we are going to use the thermal discomfort. So we are going to inspect, we are going to analyze whether the integrand of that discomfort has increased over time. If we detect that it has increased, if we detect it has not increased, if it's equal than the previous objective integrand, then we give a reward to our agent of 1. If we detect it has increased, then we don't give any reward. Okay, so that's the way we define the reward, which is a very important step when defining the algorithm for reinforcement learning. Now, what we are going to do is that we are going to instantiate that BOPTEST-Gym custom reward. Okay, NumPy is not defined because, yeah, of course, I didn't import it because I didn't run the exercise. So NumPy as MP. Okay, I need to use some part of your exercise. So name is not defined. It's in why name is not. All right. Here we need to find this. Okay. So once we have defined our environment with a custom reward, we instantiate it. So we do as before. Action space is the modulation. Observation space is the temperature of the zone. We want to discretize it. Here I'm explaining how to discretize the observation space. So there are different ways of doing so, depending on whether you want the values outside the bins to be part of the observation space or not. In this case, we want. So basically what we are defining is an observation space of dimension 3, which is going to tell us whether our temperature is below the comfort set point, in the comfort range, or above the comfort set point. So if we are here, we are good. If we are here, we are too hot. If we are here, we are too cold. Basically, that's what it means. And now we are going to learn. Oh, I didn't define, I didn't call the cell here that defines our Q-learning agent. Now I'm going to learn the, here it's already called, for 10 episodes of experience. So here what I'm going to do is to interact for 10 episodes that I have defined here to be of 2 days. Yes, 2 days. And so for every episode, once every episode is done, we are going to get a print that displays the evolution of the temperatures. So I didn't mention, but gymnasium environments typically allow to render the evolution of learning. So that's very handy. And in that way, you can see whether your environment is doing something useful or not. So here we get the first episode. You can see that it has been randomly initialized here because we have decided to, well, we have set it to be rendered, as I was saying. And we define a random start time to be true. So it just happened that it initialized our building to start this date. I think it's 12th of January. Okay. It's applying some random actions to it, for which it's every time getting some rewards. So the reward you can see here, it's one if we remain inside the comfort range that we have defined, or it's zero, so there is no reward in case we are outside for whatever reason. So these values here are going to shape the our Q function, which in our case, as in the graph I was showing above, is just one-dimensional, because we have just one-dimensional observation space, which is our temperature, and one-dimensional action space, which is our modulation of the heat pump. And every time I'm printing here what is the Q value of being in a specific state and taking specific action. So what you can see here is that, for instance, for observation three, if we are too warm, I believe, yeah, that's the case, because that's the only, when we are too warm, that's the only case we have experienced here. If we apply no action, so no activated heat pump, that has some value. Whereas if we apply the heat pump modulation to be 1, that has no value. So it has less value than activating, which makes sense. So that way it keeps learning. And you can see also, since it didn't have lower discomfort, it has nothing to say about that case of experience. So it will keep learning. It's already in episode number 5. But on the meantime, I'm going to explain. It should go for 10 episodes. But on the meantime, I'm going to explain how we can interpret this. So I'm just plotting here what is, I'm trying to display what is the Q function so you can see it. So this is related to what I was saying before. You can see that if we are, for instance, too cold, after we have learned these episodes, we can see that the agent has learned that that it has more value to apply action 1, so modulation of the heat pump full power, than just not activating it. And if we are too warm, it's the opposite. We prefer not to activate, we prefer not to activate than activating it. Whereas if we are in between, if we are at the comfort range, it doesn't really distinguish whether it's better or not, because it's not as smart, because we have provided with very little data. Actually, the reason why we are learning this is because we want to showcase or to demonstrate how reinforcement learning agent can learn something from data, right? But actually, this is very silly. This is something you could have learned by your, or you could have learned by your own. But you're seeing here how the agent can has some learning capabilities. Here I'm just explaining that the value function is what is called the projection of the state value function in the state space. Not it has not two dimensions, so not state action space, but only in the state space. So you can see that the most value is to be in the comfort range, and here what you can do is to test your algorithm. So I'm not going to run it just yet because it's still learning. It's in the episode 7, 8. Okay. So you can basically, once you have learned, instead of using the learn method, you can use the predict method with deterministic equals true to exploit the policy that you have learned. And if you do so, you will see that it will be using the Q function here as to decide on the action. So every time you get an temperature below 21 degrees, is going to start the heat pump at maximum power. So the last fill in the blank exercise, which is what we are going to finish with, is for you to improve on the learning. So you can try out several different things. Actually, this is something that's not set in stone. There's not a specific answer to it. But I gives here some recommendations. You could, for instance, tune the reward to return a reward of -1 instead of 0, in case you want to penalize whenever you are outside of the comfort range. You can also tune epsilon min, epsilon decay, alpha and gamma, so the hyperparameters of your Q learning agent. And you can also try out other things like increase the state observation space, like for instance, instead of using just that discretized action wrapper with 1 bin, you can use 10 bins. So different to have more granularity on the action that you can take for the heat pump. Or you can augment the observation space with things like ambient temperature, solar radiation, internal gaze, electricity price, and even make those predictive. So I'm inviting you here to fill out that observation space that is more complete, and you could use the the information that you gathered when interacting with BOPTEST that you requested to get the inputs and measurements. And then you just have to normalize and discretize observation and action space as we were doing before with as many bins as you like. Then just instantiate your reinforcement learning agent. Here, I'm leaving that blank in case you want to use more advanced reinforcement learning agent, for instance, from stable baselines 3. And after that, you may want to learn, at least for just to check that you can actually learn from some episodes or time steps of experience, just to check that all the formulation you are deploying here is correct. But what will be nice is that you make sure that you at least print what is the observation action space that you get with your new environment. Okay, so hopefully this has finished already. Yeah, this is done. It's learned with the 10 episodes, so we now would be able to run also all these cells that we didn't run before. So that's it. Thank you very much for your attention. I'm going to stop sharing and stop the recording, and I hope you have a lot of fun with BOPTEST and BOPTEST-Gym. Bye.